Well, good evening. Tonight we're going to work on combining all the information we've learned the past couple of nights about the first and second derivatives. We're going to take everything we've talked about as far as increasing, decreasing, maxes and mins, as well as concave up, concave down, points of inflection. We're going to kind of throw it all together, and then we're going to finish off the night by talking about some rates as they pertain to some real-world problems. So the first example I've got cooking here is I pulled up a funny-looking graph, and I've labeled 4 specific points. And I want to go through and I want to just talk about each point individually. And I want to talk about, when we look at point A, what can you tell me about the first derivative and what can you tell me about the second derivative? So first of all, and let's assume this, and I should probably write this before I write anything else. Let's assume that this is a picture of the original function f. Of course, if it was a picture of f prime or f double prime, that would really change things. So let's say that f prime measures the slope at A, the instantaneous slope, and as I visualize a tangent line, I definitely see a positive slope. So I'll say the first derivative is positive, and then the second derivative is going to measure the concavity, whether we're concave up like a cup or concave down like a frown. And I would say at point A, we're definitely concave down, so I'm going to say f double prime is negative. Alright, next one. Let's go to point B. First derivative, it looks like the curve is definitely decreasing, so I'll say the slope's negative, the first derivative is negative. Now, the concavity is very, very tough to tell, and in fact, it looks like B seems to be the midpoint between the max and the min, and so I'm going to say, at least that was my intention when I put it there, I wanted B to represent the point of inflection, so I would say that the second derivative equals 0 in that case. Let's see, let's go to C. When we're looking at point C, looks like the first derivative equals 0 because we've got a horizontal tangent line right there. And as far as the concavity goes, it looks like we're definitely concave up like a cup, so we're going to say the second derivative is a positive number. And then last but not least, we'll lock in on point D. And the first derivative looks like we're just past the max, so our slope is negative, first derivative is negative, and it looks like we're concave down again, and so we'll say the second derivative is also negative. Alright, it's time to play a very famous game, and this game is called Can You Draw the Following? And so number one, I want you to draw a picture such that the first derivative is always positive for all real numbers, and the second derivative is also always positive for all real numbers. So translate that. We need to draw something that is always increasing and something that is always concave up. I think we can do it. It would be a curve that looks like this, and we would say that this curve is increasing at an increasing rate. Alright. Okay, let's take a stab at a very similar one. Number 2, I want you to draw a picture that has a first derivative who's always positive and has a second derivative who is always negative for all real numbers. So, translating that into English, we need to draw a picture that is increasing but concave down. So let's see, we're concave down, something just like that. So we'd say this function, yes, it is increasing, but at a decreasing rate. Increasing at a decreasing rate. Alright, let's try. Told you this was going to be a fun game. Let's try number 3. Let's draw something such that the first derivative is always negative and the second derivative is always positive for all real numbers. Translating that in English, we need to draw a picture that's decreasing yet concave up. Do you think that's possible? Well, let's put our thinking caps on. Let's see, and we might have to, pencil's always a good thing. We might have to draw something and then take a step back and see if we like it or not. But I'm going to draw something that's decreasing and curving this way, and that would kind of give me that concave up sensation while it's decreasing. So we're going to say that this one's decreasing at a decreasing rate. So we'll say decreasing at a decreasing rate. And it's just all because we're starting to kind of flatten out there, and we're starting to simmer down, as we like to say. Our fourth one, and I bet you can feel what's coming here. Yeah, we want to try to draw a picture such that the first derivative is negative for all values of x, and the second derivative is also negative. Translating that into English, we need to draw a picture that's decreasing and concave down for all values of x. Decreasing and concave down, all right? Something like that. So we'll say this bear is decreasing at an increasing rate. So those are the four scenarios that we could potentially, that all curves will fall into at some point. Alright, I'm going to show you some really weird tables. In other words, they're giving us very limited information about f. And so you can see right here in the table, this is all they're telling me about f is just 4 separate points that lie on the graph of f. So here's what they want me to do. They say, oh, it's a differentiable function. Good, it's continuous. Strictly monotonic means there's no maxes or mins. It's either only increasing or it's only decreasing. There's no maxes or mins, and it also says there's no inflection points here. So they're taking a lot of fun out of it, you could say. But they wanted me to determine the sign of f prime and f double prime. So we're kind of try to visualize those last 4 examples we just did and see if this table fits one of those 4 examples. And of course, if all else fails, we can always plot these points as well. What I like to do is I kind of like to add an extra column here to the table, and I call these my estimated EST f prime values, okay? And what I'm saying is between these 2 points right here, it looks like my slope, my rise over my run, is going to be a 3. And then between these two, it's going to be a 2, and between these 2 points, it's going to be a 1. So, judging by my table, all of these estimated f prime values are indeed positive. So we know f prime's positive. We can say that with confidence, okay? Now, how do we make a judgment about f double prime? Now remember, f double prime just happens to be the first derivative of f prime. And it looks like to me, f prime is decreasing. So that means his derivative, f double prime, is going to be negative. So, going back to our pictures, we're going to say that this function's increasing, but at a decreasing rate. Okay, very similar to the last one, same set of directions. Here's a table. F is differentiable, it's strictly monotonic, and there are no inflection points. And we want to try to figure out whether f prime is positive or negative, and then we'll try to figure out whether f double prime is positive or negative. So like I said, I like to kind of add that extra column, and I'm going to do some estimated values of f prime. And that first point looks like my rise is going to be 3 and my run is 2. So I got 3 halves, which is about 1.5. The next set of points there, my rise is 5 and my run is 3. So that's going to be about 1.6 repeating. And then my third set there looks like my rise is 5 and my run is 2. So that's going to be about 2.5. So judging by the table, my f prime values are all clearly positive. Alright, so we'll say f prime of x is definitely positive, and this time these f prime values, they're increasing. So they're getting bigger as we go down that table, which means f prime's derivative, f double prime, is going to be positive as well since f prime was increasing. So I'll write that out just to make sure we're getting that. If f prime is increasing, that implies that f double prime is positive. Alright, maybe we could even take that a step further. What if I told you that the 10th derivative was increasing? You would then know that the 11th derivative, whoops, that's not a double prime, take that as an 11, I probably could have picked a better number, of x is going to be positive, okay? So just to wrap this one up, it looks like we're going to be increasing, f is increasing because that one was positive, at an increasing rate because the second derivative was positive. Alright, here's our third table, and same set of directions. F's differentiable, continuous, strictly monotonic, all that jazz, and we're going to try to figure out whether the first derivative is positive or negative, and then the second derivative as well. So I'm going to estimate some various first derivatives, rise over run. Let's see, I got a rise of negative 5 in a run of 2, okay? Rise of negative 4 in a run of 2, and a rise of negative 2 run of 2. So it looks like I got negative 2.5, I got negative 2, I've got negative 1. Okay, So we just proved that all of the first derivatives are negative, they're less than 0. But how would you interpret f double prime? Well, what's interesting is as you go down this list, these numbers are increasing in value. And I know that might bother you a little bit, but if you picture your number line, and you plotted these three numbers, you would be moving from left to right on that number line, thus increasing. So I'm going to make the argument that because f prime is increasing, the second derivative is positive. We're going to say that the function f is decreasing at an increasing rate. Well, I know you're having so much fun with these tables, I figured we'd do one more. And these tables have been quite popular on these more recent AP exams, the ones that have been released in the last 10 to 12 years or so. So let's estimate some f prime values. We got our, let's see, rise of -1, run of 3, rise of -3, run of 2, and, oh boy, rise of -9 and a run of 5, it looks like. All right, so that would be -0.3 repeating, -1.5, and -1.8, it looks like to me. Okay, so clearly these numbers, these measurements we've gained from f prime are negative. And how would you interpret f double prime? Again, if you pictured these numbers on a number line, you'd be moving from right to left. So I think these numbers are decreasing, and if f prime's decreasing, the next derivative will be negative as well. So based on that, we could say that f of x is decreasing at a decreasing rate. Okay. All right, we're going to try to squeeze in two real-world problems here before we call it a night. And we're definitely going to have some calculator active questions. So I should have warned you at the beginning of the video, but if you have your calculator somewhere in the house, just hit pause, go grab it, and then run on back here, and we'll dive into some of these problems. But here's what the problem says. It says traffic flow is defined as the rate. Now that word rate is going to be really special, okay? It's the rate at which automobiles pass through an intersection measured in automobiles per minute. So we're just keeping track of how many automobiles are going through the intersection each minute. The word per is directly associated with the word rate. I don't think we'd ever use the word rate without also using the word per in the units there somewhere. And they said the traffic flow at a particular intersection, maybe the corner of Clark and Bayview or something like that, is given by this function right here. Very strange looking function, okay? And they basically said, hey, is traffic flow increasing or decreasing at t equals 3? Now when they said traffic flow, all right, they are referring to f of t. So basically, let's reread that sentence. Is f of t increasing or decreasing at 3? So what I need to do is, anytime we discuss increasing or decreasing, we're talking about that function's derivative. So I'm going to have to get my hands on capital F prime of t, which I'm visualizing some chain rule here. We're going to go 1/2 times 4, which is 2, x plus 2 to the -1/2 times 1, plus sine of pi times x times pi, and then the 10 is dead. And then what I'm going to do is I'm going to evaluate this derivative at 3 by plugging it into my calculator. And of course we're in radian mode. And my calculator is telling me it's 0.894. Most importantly, we just want to focus on the fact that that number is positive. So we'll say that the traffic flow is increasing at t equals 3. We don't really specify just at that moment because f prime of 3, not f prime of t, but f prime of 3 is positive. Okay, that would be my reasoning. All right, next. They want to know at t equals 3, is traffic flow increasing at an increasing rate or increasing at a decreasing rate? Okay, and I'm going to cross off those other two choices just because we've already proved in part A that it's increasing. So these two choices have already been eliminated because of that work. So that just means we want to go to the next derivative, basically. And the next derivative, f double prime of t, I'm going to go through some more chain rule. Negative 1 x plus 2 raised to the negative 3 halves. Alright, and then we're going to say that's positive cosine of pi x times another pi, so now I've got pi squared as my coefficient. And now what I'm going to do is I'm just going to evaluate this second derivative at t equals 3. We'll plug it into the calculator one more time. My calculator ended up giving me negative 9.959, which is clearly negative. So that's going to put me at increasing at a decreasing rate. Traffic flow, f of t, is increasing at a decreasing rate because, and then I'm going to hit on both things here, because f prime of 3 was positive, yet f double prime of 3 was negative. So we just got to read these problems really carefully and understand what the first derivative is going to help me with, and then be able to understand what the second derivative is going to help me with. Okay, our last example for the night, then in this one we're going to have to be patient with. This might make our head spin just a little bit, but we're going to sort this one out. And it says the rate of change, okay, for the number of mosquitoes on Malaria Island at time t equals t is modeled by this function right here, and it's measured in mosquitoes per day, all right? Now remember, this function's a rate. It's measured in mosquitoes per day. So what they're really saying, similar to the last one, although they're not putting a prime sign on that m, this function is technically already the derivative of some other unknown function, okay? And again, that's what the word rate's kind of implying. So think of it this way. If we think of our normal, traditional hierarchy, we always think of f as being the original. Let's think of f as being just measuring the number of mosquitoes, period. Okay? Whereas that derivative would then measure the rate at which the number of mosquitoes is changing. So that would be our capital M of t. Okay? And then if we took f double prime, that would be equivalent to m prime, or in other words, that would be the rate at which m was changing, and so forth. Okay? So anyway, and I get to part A, they want to know, is the number of mosquitoes increasing or decreasing? Now, they're not asking me whether m's increasing or decreasing. They're asking me whether the number of mosquitoes is increasing, which you can think of as function f here. And the only way I'm going to be able to know if that function is increasing or decreasing is to look at his derivative, which just happens to be m. So this is already the derivative we need. We don't have to take another one yet. So I'm going to say m of 6 equals 36 times the sine of pi divided by 6. And I'll tell you what, that looks like it's clearly a positive number. It's going to be greater than 0. So we can go back up and say, well, the number of mosquitoes is going to be increasing at t equals 6 because m of 6 was positive. And really what I want you to take out of that is recognizing the need that this function m of t was already the first derivative with respect to the number of mosquitoes, so I didn't have to do one by hand. Now, keep that in mind here as we go to the next one. They want to know at t equals 6, is that number of mosquitoes increasing at an increasing rate or increasing at a decreasing rate? And just like the previous example, we're going to cross off these other two options because we've already proven that they can't be there. And so we're going to go to, basically, if f is the number of mosquitoes, then we need to go to f double prime, which is going to be m prime. So we're going to need a little what rule? What rule are we going to need here? Yeah, I think we're going to need some product rule. And so let's see if I can get this right. We're going to say the first times the derivative of the second. So we got cosine of pi over t times the derivative of the, whoops, gotta grab that pen. The derivative of the inside. Now, that's going to be negative pi t to the negative 2, because I'm picturing this function right here as being pi times t to the negative 1. So deriving the inside wasn't as easy as I would have assumed it was. Plus the second sine of pi over t times the derivative of the first, which is 2t. Now what I'm going to do is I'm going to plug the 6 into that bar and see if I get a positive or a negative answer. And after some careful calculator work, we got 3.279, always going 3 decimals, which is greater than 0. So now I can say, well, the number of mosquitoes is increasing at an increasing rate because m of 6 was positive and m prime of 6 was positive. Okay. Now we're going to go over in class tomorrow. We're going to just because the video is getting a little long here tonight. I want to bring your calculator to class tomorrow. We're going to talk about how to evaluate derivatives on the calculator without actually having to take this derivative, which, of course, if it's on the calculator active section, we're going to need to be able to know how to do that. So we're going to introduce you to the math menu and what choice 8 brings to the table. So it'll be a very exciting day tomorrow in class with those calculators. So have a good night, and we'll catch you tomorrow.